All right. Good morning or afternoon, depending on what time zone you're in. We're back for the NFL Big Data Bowl 2025 series. First, we'll start out by going through a recap of everything that we've done so far. Then we're going to add some visualizations for the receivers and the defensive coverages, just to get an idea of how they actually match up against one another. And then work on adding the defender information into the models that we have, as I think that would be a good way to get improvement on our predictions so far as the route combinations or coverages. And then work on doing a little bit in creating visualizations of a play moving as it moves in real time in Python. So if we can get through all of that today, I think that would be great progress. If not, the visualization last part may take a little bit longer, and we can always come back to that either in the evening or tomorrow. So let's dive into what we've done so far. So this is for the NFL Big Data Bowl 2025, hosted by Kaggle. The idea here is to use any information that you know before the ball is snapped to predict what will happen after the ball is snapped. The first versions of our models focused on um, predicting run versus pass, which it did fairly well. We were at about a 75% accuracy rate with very basic data. We're not doing a lot of complex transformations on the data that we're learning. Another way you could potentially make it better is to also incorporate like the weather data for it. You know, if it's raining or snowing heavily, teams are way more likely to be running the ball just because it's that much harder to throw or catch the ball in those situations. So just an idea of like more public data that you could add to it, but this is just working off of the base data sets that Kaggle provides to you for the competition. So we start by just importing the libraries that we'll be using throughout here. So it's a good idea to make sure you have pandas, numpy, matplotlib, seaborn, and then sklearn. sklearn provides a lot of the models that we're going to be using. It also helps us to do the one-hot encoding and the scaling of our numerical data. And then we pull that all together. There will be different models. The first one that we use is logistic regression, but then we'll do things like support vector classifier, random forests, and decision trees. And then the metrics function here is so that we can get an idea of the accuracy of our model and then look at the classification report to get an idea of how those predictions actually break down in terms of precision versus recall. After that, the next step is to make sure you import your data. This is how you would import each of the main tables here. And then this is the tracking data. You'll want to start pulling this in now because we're going to be using that in the visualization portion. The first, I think it was 2 videos in the series, was going through just doing data exploration and understanding the data set better. Whenever you're doing this for a project yourself, you want to make sure that you understand the data. You want to make sure that it is fairly complete data. Otherwise, you will have to think about how you're going to handle things like null or incomplete or unbalanced classes in your data. Overall, this is a fairly balanced data set in terms of run versus pass. Now, once you get down to things like the offensive formations and the route combinations, those are going to be more unbalanced just because it's the tendencies of those teams that compromise or are composed of your in your data set. So you'll see here the data set is pretty well cleaned up. It's way better than you would get if you got a data set in the wild. You can see here that for the most part, all the data is complete here in this plays table. And you can see there's a few here where the yard line side is null. This is actually because this is happening at the 50-yard line, which is there's no team assigned when it's at the 50 because it doesn't favor one team or the other, or it's not in that team's side of the field. And then you'll see a few plays here where there's no offensive formation or receiver alignment. These turn out to be the kicking plays during the game. And so there is no formation or alignment on those because the formations are fixed. You can see here there is a play clock at snap where there was no value. This is because there was one play during the season where the game clock had expired and there was a penalty. So they got a free play without the clock on, and that's why you have one there. And then you can see here the the pass result and length. Well, that's because not all the passes are completed, and that's why you can see a difference in the result versus the length. And then these ones without pass results, well, those are the rushing plays. Then we started to look at the data itself to try and get some summary numbers to see how well we can understand the data set itself. And what we saw here quickly is that if we just tried to pull in the rushing yards on a given play, it gave us an extremely low number. What was happening here is that all 22 players are represented in this data set, but only one has rushing yards. So the best way to get to that actual mean would be to do the filter for who had the rushing attempt, and that would give you who had the or what the average rush distance was. In this case, this was 4.56 yards. Same thing happens here on receiving yards. We needed to find out who had the pass reception, and then we see that the average pass completion results in about 10.9 yards per completion. And do be aware that this is completion, this is not pass attempt. So the receiver had to have catched the ball for there to be receiving yards, and that's why you can see here that it's 10.9. Then we started to group these numbers together based on the teams, just to get an idea of who performed better, who performed worse, and an idea of how those numbers actually vary from one another in terms of the average. And what you see here is that Chicago averaged about 4.5 yards, or sorry, 5.5 yards per rushing attempt. And then you have a team like Tampa Bay, who was the worst, and they were just under 3 yards per rushing attempt. Very similar thing here for the pass receptions as well. You can see Miami had the most yards per completion, and then began to work to group together the data sets to get a better idea of, okay, well, we know how many rushes that they had. How many times did they actually rush the ball? And this gives you an idea in terms of single outliers. What ends up happening here is you can see this player had a single rush for 44 yards, so it was likely some trick or design play that was catching the opposing team by surprise. And then you can see the outcome here in the negative of that, where they tried some trick or variant play and it ended up hurting the team, right? And so they only did these a few times through the season. So then the best way to handle this is to set a minimum number of plays to get an idea of like who the best rusher was on average. And what you see here is I set the number of 10, and that's kind of just an arbitrary number to help get rid of some of the outliers. But you can see there are still players that are right up against that that arbitrary cutoff that I said. So you see Jermichael Hasty here has 11 rushes, which is the absolute bottom of the set here, and they averaged about 7.9 yards per play. Now, this isn't going to tell you, for example, like who the best running back is for that season, because a running back will have, between 20 and 30 yards or 30 attempts per game. And so you would expect those average rush numbers to be more towards the actual average that we saw earlier of about 4.5 yards. Another thing that I was curious about, and we ended up incorporating into our models, was is there motion on the play by any player that will help predict run versus pass? And so to do that, I created a flag field here called motion since line set. And this goes through and it checks every single player on a given play if there is a motion. And then we group that together and we set all of those rows to actually be flagged as there was motion on that play. Then once, as I said earlier, we were talking only about pass reception. Well, we had to change it to include all pass attempts. So we needed to find out if there was a drop back on the play, and that would tag the play to the quarterback. And then we needed to use this pass reception to get what the receiving yards were on a play. And then we group them together here in the merge set. So that way we have an idea of all the rushing attempts and all the passing attempts in a game. So now we're getting more complete data. Then we got the player names added into the data set, and then we pulled in more of the contextual information on a given play. So the offensive formation, the receiver alignments, quarters down, yards to go, the time in the game, and then the scoring information. This helps to provide more context to the model in terms of everything you would know before the ball is snapped and the given situation of the game, right? Teams are going to be handling the game differently when they're down 2 scores versus when they're up 2 scores in a game in terms of doing passes or rushing and then the routes that they're running. Hey, Patrick, thanks for the comment. And yeah, please feel free to come back after and we'll go through everything. Like I said, the plan today is to talk through, right now we're covering everything that we've done so far. Then we're going to work on adding some visualizations and then adding defender information into the models themselves. Then the next thing here we tried to do was to add all the players on a given play to the data set just to have an idea of who the 11 players were on the field when a play happened. The idea here would be that this would help us to get better predictions by knowing, oh, a certain player may be on the field on a given play type versus others. And what we ended up seeing is that that didn't actually help the model, and we'll cover that a little bit later in terms of its predictions. So now this is what our full data set looks like. So you can see the player ID, the game and the play ID, and then the rest of the information here, rushing, receiving yards, and then over towards the end here, who those 11 players were on a given play. Then I started to add some visualizations just to get a better idea of how each team handles their offensive formations. Each team, like I said, is going to be a little bit different in their approach, and you can see that played out here. So you see, for the most part, teams generally ran with a lot of shotgun and single back formations, with a few exceptions. There are some teams that heavily ran the pistol instead of the single back, and those were teams like Atlanta and Baltimore here, and then a few other teams had mixed it in a bit compared to others. So you have teams like Philadelphia, Seattle, even San Fran here, and Arizona were attempting to do more pistol and a little less of the single back formation because of that. Then I tried to lay out how each team performed on the offensive side of things. And so this is just a layout of the average pass yards by team versus their average rush yards. The idea here is that you want to be in this upper right quadrant. Everything up and to the right is better. You'll have more average pass and more average rush. Again, this is based on the number of, or sorry, the dropbacks now instead of being on the completion percentage. And so what you see here is that teams actually moved up. So, for example, Chicago here, we had seen earlier was much higher in terms of their average pass, and now they're a little bit back towards the pack. Uh, Miami here was up at almost 14, and now it's back down to 13 once you incorporate all the passing attempts in here. And then the goal here again is to be in this upper right-hand quadrant. Obviously, the more up and to the right, the better. And you can see here, like Chicago had such a dominant rush offense that it was also having a good pass offense. And you can kind of see almost there are diagonal lines that are kind of boxing in this data that tells you that these two are highly correlated to one another. If you have a better rushing attack, you're likely to have a better passing attack, and vice versa. You have better passing attack, you're having a better rushing attack, with some exceptions here. So you'll see, for example, Miami had a very good pass offense, but below average in terms of rushing. My guess is if their pass was worse, then their rush would be much worse, and they would be falling more down in line here. Same thing for Denver here, higher than average pass, but below average rushing. And you definitely don't want to be in this bottom left corner because this is your offense is kind of sputtering or stumbling. And so you have a team like Tampa Bay here, who, when we looked more at their data, was very predictable in terms of rush versus pass and the formations they were using for that. So you'll see here way below the average in terms of rush yards, and then below average in terms of the average pass outcome as well. So if you're here, if you're the Rams, the Colts, or Tampa Bay, you definitely don't want to be here. And your goal is to get over towards this upper right hand corner. And so you would say like the best and balanced offenses could be over here. So you have like Chicago, Atlanta, Buffalo, and then Detroit. And then you have a bunch here more towards the middle. And then, like I said, these are your worst performing of those offenses. Then we started to work on building our models. Our very first model was very basic, I would say. You literally just had what the team was, what formation were they in, and how did they assign or align their receivers on a play. And then you were using that to try and predict whether they were going to run the ball or pass the ball. We decided if they were rushing the ball was simply if they had rush yards on the play. Otherwise, it was going to be a pass play, and that's all we were using to try and break down and predict those. This part here is how we split up the data. So we're splitting the data into 80-20. 80% is used to train the model, 20% is used for the testing, and then we're doing what's called one-hot encoding. What this does is it's creating a column in the dataset for each group in a field. So for example, the team abbreviation, that means there's going to be 32 columns here in the one-hot encoding for the 32 teams that exist. Same thing for the offensive formation. We saw there were about 8 different offensive formations, and so they would each have groups. And then receiver alignment would be the same thing. Then we put that into the model, and with that, we got about 70.5% accuracy of run versus pass, just knowing 3 fields. So knowing what team it was, what their formation, and how they set up their receivers gives you a 70% outcome on correctly predicting whether they were going to run versus pass. And then looking here at the classification report, you can see there's a bit of variance between these two numbers. They should be much closer to that average of 70.0 or 71. And we're a few points off. So that means that there's more information that is available in the data that would help us to predict this. There's always going to be some variance here where you're not able to explain what's happening with the information that you have. But this is, we're about 3 percentage points off each way from the mean here. So there's definitely more that we can do to get them. And so we work to expand that regression model. Like I said, you're going to treat the game differently, whether you're up 2 scores or down 2 scores. So I use the scores here to add a score differential column to the data set. The first thing we need to do here is check if the team abbreviation here matches the home team. If so, then we're doing the home score minus the visitor score to get the idea of the game score. And then if they're the opposite of that, or the visitor, then we're doing their visitor score minus their home score. So it'll be negative when you're down, it'll be positive when you're up, and that helps to provide more information. I also did some experimentation here on bucketing the yards to go and the absolute yard line number. Yards to go is the number of yards needed to get a first down, versus the absolute yard line number here is the yards needed to score a touchdown. So what you see here is, in terms of the yards to go, I made some very basic buckets, and this is similar to what you hear when you're watching a football game. You'll hear it'll be like 3rd and short. That typically means that there's 2 or less yards to go to get a first down. And then 3rd and long, you'll hear usually it means that there are 8 or more yards to go to get a first down. And so those are just kind of the 2 buckets, and then everything else falls into this mid bucket. Very similarly, for the absolute yard line number here, 20 yards to go means that you're in the red zone and you're more likely to score. It also means that the field is a little bit shorter in terms of what you have available. So sometimes it's harder to actually pass the ball in these situations. So put everything in the red zone under the short bucket. And then I had just set 50 yards arbitrarily here. You could probably take this down to about 40 yards in terms of long, because the idea here was that you would no longer be in range to attempt a field goal at this point. And so I called that the long bucket here. So you're out of kicker range. You're basically in an area where you would punt the ball instead of trying to go for it on 4th down by having it at 50 yards here. Then everything else falls into this middle bucket again. Another thing about the data here is that the game clock only tells you the clock or minutes and seconds remaining in a quarter. So it doesn't tell you the full time that is left in the game. So if it's the first quarter, I add 45 minutes to that clock. If it's the second quarter, I add 30 minutes. And then 3rd quarter, I add 15. Then if it's the 4th quarter, we're just leaving it exactly the same. But then in football, there are the 2-minute warnings before each of the half. I separated these because it actually is a little bit different for teams in a game. If you're in the final 2-minute warning and you're down by 2 scores, if you're the offensive team, in this case, and you're down by 2 scores, you're going to treat the game way differently than you would otherwise. But if you're the team that is ahead with 2 minutes, you're going to be what they call running out the clock. And so you're likely to run a few plays or kneel down the ball, and then basically take your win. And that's what you see here is why there are so many less plays here in the final 2-minute warning versus that halftime 2-minute warning. The reason being at halftime, teams are always trying to add more points to the board. So here, when these 2 minutes, you only have that much time remaining to actually score before you either have to restart your possession or kick it to the other team with the beginning of the second half. And you see here, there's about 13,000 plays, or yeah, sorry, 13,000 total plays in the data set. But then if you look here at halftime, 750 plays were run. And then near the final 2-minute warning, a little over 500 plays were run. So over 10% of the plays happen here in this 4-minute window out of the 60-minute game. So you can see here how teams are already trying to treat these much more differently. And I thought that would be important to the model. So then with our updated fields here, we now have a more complete model. So we still have that formation, team abbreviation, receiver alignment, but now we're adding information like what quarter it is, what down is it, that yard bucket for short, medium, or long distance. Same thing for the distance to goal. Was there motion? And then how much time is left in it? Is it the regular time in the game or in that halftime or final 2-minute warnings? And then we're still trying to predict whether it's rush versus pass. So that is our target here. Again, the same one-hot encoding and scaling apply here. And this actually gets us up to 74.1%. And when we look at the classification report, we're much closer together towards that middle or that 74% now. There's precision recall are exactly the same here. So we've got pretty good completeness in terms of the data, and it's only giving us that 74% accuracy. So then I thought maybe it makes a difference in the data set here to know who the players are in terms of the offense on the field. So I just called them players 1 through 11, exact same other fields before, and then brought this into the logistic regression. And what we see is that the model accuracy actually goes down here. So we were 74.1% before. We actually lost 0.2% accuracy by adding in the data here. And that's because this isn't helpful enough to the model to actually help it determine whether it's a run versus pass play. A lot of the player information is already gained by having this other information here. So likely by knowing who the formation is or what team it is, or receiver alignment provides a lot of the same context as knowing who those actual players are. Then instead of using those yards to go, that yard bucket or the yard or distance bucket, treating those as a number, would that actually help our data set? And what we do see here is that that does actually improve the model. So we're at 74.4% accuracy by changing those back to numbers instead of using the bucket. And then a very similar thing here, but including all the players now. And we see that once again, this brings the average back down to 73.8. So it's not very helpful to know who the players are, and that means that we're getting that information from other parts in our data set here. So then I tried to add a few other versions of models here just to see if we could get a better predictive power. Like it says here, the random forests, it typically will have stronger predictive power, but it will have lower explainability. And how random forests typically work is you can shove all the data that you want in here from your data sets, and you should get better predictive power, but at the cost of not being able to explain what's happening in the models as easily. And what you see here is that this is a scenario where actually knowing who the players are helps the model. You'll get about 74.4% accuracy once we know the players and then all that same context information. And not having the players here is a 73.5%. So this is a scenario where actually adding the players added more information to the model here. And then just another model for comparison, this is the support vector classifier. It's very similar to random forest in terms of it's a little bit harder to explain what's happening here, but we saw that the accuracy was only about 73% once you had the players, and then without it was actually about 70%. So not a very good predictive model in terms of trying just to predict the run versus the pass here. Then we started to shift to trying to predict the routes that the receivers were running, just to try and make it uh, more complete in terms of what we're able to do with the data set, getting to about 75% accuracy in terms of run versus pass. It's pretty good. There's probably a lot of information that we would add to it. Like I said, including maybe the weather data could add more predictive power. But it was a good experiment to kind of get more familiar with the data set and then move into something that would be more challenging. So in terms of the route predictions, tried to add who the defending team was on onto the data set. So knowing this information, we could actually take this and go back to the run versus pass scenarios to make a prediction because we didn't have that information in there before. We really only had who the offensive team was on those given plays. Then we also added if the player was running a route, then we tried to have an idea of how many receivers were on the field, how many tight ends, and how many running backs for a given play, just to add more information to our data set. And then we merged all that together with our information from before. So what you'll see here is this ID is the receiver who is running the play. How many running or wide receivers were there on the play in total, the tight end and then the running backs? And then adding all the same information. So the team abbreviation is the team that receiver plays for. The ID here is their quarterback, all the player information, whether it was a rush, what's the score differential in the game, and then all those same fields from before. And then this time we're also including who the defensive team was. So this was Buffalo versus the Rams here in terms of this game. And then this one was like New Orleans versus the Ravens. And so we fed that into the model. The idea here was that because we're no longer in a situation of run versus pass, which logistic regression should be very good at, we're now in a situation where there are this is about 10 different routes that a receiver can run on a given play. And just feeding all that information and into the model, what we actually see here is that the accuracy was about 30% in terms of being able to directly predict run versus pass. But then if you look here at the classification report, you kind of see what's happening here. There's so much variance in a given class in the data set that it's not correctly, or it doesn't have enough information to correctly make the predictions that it's trying to make. A similar thing here for the support vector classifier, very similar. This is 29%, 0.2. Similar situations happening here. It wasn't even predicting some of the routes that were actually being run in the data set as it didn't have enough information there. And then I thought, well, because the other models weren't performing as well, maybe the random forest classifier could do better, but it was not doing so in terms of it. And you can see here what ends up happening is it highly predicts certain classes and then does not predict the ones as well. And I thought, well, since we hadn't included the player data and it helped some of the models before, let's include that information. And you can see here, again, the logistic model actually goes down, knowing who the players are. The more vector classifier also goes down. And then in terms of the random forests, well, it's still not performing. It's performing slightly better, but it's still not in the same ballpark. You can see here, it's only got about 21% accuracy now at the time. And so we added in the fourth model to our set here. This was the decision tree classifier. The idea here was that we can also get a better visual breakdown of how it's trying to come to the conclusions that it's doing to make those predictions and try and see what it's using to predict the information here. One of the things that you do have to do here with the decision tree classifier is tell it how many times it can split the data along the way in the data set. So I did some experimentation to try and find out what would be a good result here. And what we see is somewhere around 7 to 8 splits is around the best. What happens here is that we fall off, we come back up a little bit, and then there's like a little bit of wave pattern until it eventually evens out here. You can see at just having 24 splits being allowed. So I just chose 8 to put in here. I know it's slightly worse than 7, but the idea here was that we could go through and get better. What you see is the decision tree gets about 26% here. And part of the reason why is that it's heavily favoring predicting that a route is going to be a go route. It will occasionally predict others, but for the most part, it's predicting go in terms of the routes here. And so it's heavily favoring one. Sometimes it's barely predicting another one. You can see here the hitch route. It predicts it a whole 3 times in the data set. Um, and when it did, it wasn't very accurate when it was doing so. Same thing for some of these other routes that was heavily favoring predicting a go route in terms of it was about like 50 to 60% of its predictions. And then we pulled out what rules that the data set had come up with. And you can see here when there are certain players, it heavily keys in on those in terms of making a breakdown in terms of the routes that it's going. And so this is the full visualization here. It's hard to we couldn't make this any clearer, but it's very blurry here in terms of what it's actually doing for the split, and that's why we wrote out the rules here. So you can see we'll kind of follow this tree all the way down. So there are 3 receivers here. The formation is a 2x2. Here's the 4th receiver. If there were less than 28 of the time and the defending team was Dallas, well then and if they did not have motion, it was a route or was a slant as far as the route goes. And the same thing if there was motion. And so what's happening here is that the decision tree classifier is keying very specifically on certain plays in terms of its outcome, and that's why we're only getting about 20% accuracy. This could be far more improved. And so one of the steps that I wanted to do was to add information about who the defensive players are to the models to try and see if that would help. So what we'll do then is we'll group together the information here on who the defensive players are, and then we'll do some visualizations in terms of looking at like coverages for the receivers on a play and see if that affects things. And then we'll work on incorporating those defenders into the model. I'll come back up here to how we added the offensive players. Went too far. Yeah. So we got like I said, the receivers on a given play, but now let's go through and we'll add things for the defenders. So the receiver data here was that the player was running route. Let me see if there is defender information on a given play. Does not look like it. Then what we can do, it'll be a little bit slow in terms of running through it, but we can add, um, we'll just have to go off of the base player play data set. What we'll do is defender player play. We're going to then group by same setup here, game ID, and the play ID. And we're going to do an aggregation. Now, very similarly, notes here. You want cornerbacks. Close that out, and then we're going to have to do the same thing For the other positions, linebacker, those are LB. We have what? Defensive line and safeties. Hi. Once that closes, okay, fine. And then I realize here, player play. And what I want to know is the game ID, play ID, NFL ID. And then we need to merge the data sets here. Let's do player position data. Hmm. Fix this up. Hey, Len, let me read your question out. So you just got into football analytics, but all the stat and gameplay of American football is too new for me. You have any recommendations to learn more about NFL analytics? Some of it is just watching and learning from other people who are doing analysts. There are a few good people who do really good breakdowns as well. It's kind of depending on what your level of familiarity is, saying kind of you're new to it. So I would look at some of more of the high level breakdowns. You'll see a lot of these on ESPN and SportsCenter. When they're actually at the screen describing a play, sometimes you'll see them kind of talk about what the defender is doing on a play or how the offense had or the reasons why they had a big play. And those are, I think, really good to help you get a better understanding of what's going on. There's also some very basic videos that you can do in terms of understanding things like the different formations that they're doing. Even just sitting and playing with this data set, you'll get a good idea in terms of how teams are different from one another. Like if we go back to this visualization here, in terms of the team's formations, you'll see that while there is some variance across them, a lot of teams do very similar formations and concepts from those. And then you'll see that there are some outliers here in terms of like Atlanta and Baltimore that run the pistol formation here instead of doing a lot more of the single back. And so if you were to try and understand pistol, well, then you would want to look more at highlights or people breaking down like why Atlanta did better or Baltimore, because they'll typically talk about their formation in terms of like using the pistol versus the single back. Another thing here is that the reason, well, I can explain this one a little bit. The reason why they use the pistol formation a lot is that the quarterback is a threat to run in their offenses. And so the pistol formation allows them to add an extra um, running back to the backfield and gives them options to do or how they want to handle the run. The quarterback, when he takes the snap, could hand the ball off to the running back, or he could fake that handoff and the quarterback himself could take off and run. And by having an additional running back on the field, it adds an additional threat that the defense has to account for. And then you'll see here a lot of teams prefer the shotgun. The reason for this is that it allows the quarterback to back up from the line to get a better view of the field so they have a better idea of what's happening. A lot of times when you're lined up right under center, it becomes very hard for the quarterback to see kind of what's further down the field in terms of what the linebackers or even the corners and the safeties are doing. And by backing up a few yards, it gives them better views looking over all the lines to understand what the defense is doing. And then you'll see this is why I included motion in the data set. The player or the quarterback will then have one of the players move to try and see what the defense is doing in relation to that receiver moving in the formation. So if the defender that's on that player moves like directly with him the whole time, well, now the quarterback knows that it's more likely the defense is going to be in a man coverage versus a zone coverage. And how they approach that is going to be different based on that. So I would just say like just try and consume more of the analysis of football, not in terms of the we call them the big talking head statements where they're saying like, oh, X team is the best just because they performed that week, but actually the videos that focus on breakdowns in particular on what an offense is doing or defense is doing that's making them stand out. Because when you're listening to those, even if you don't understand all the concepts that they're talking about, it will start getting you familiar with them. And then as you consume more and more, oh, this piece that I remembered from before now makes more sense on why that's happening versus uh, before when you didn't understand it. I hope that answered your question. If not, feel free to ask another question and I'll pull it back up here. Let's go back to what was it, the expanded model. I'll go back to fixing this up. So, okay. And so this will take probably about a moment to run. The other one took about 45 seconds. So I imagine it'd be the same thing here where I can answer more questions while this is running. The idea behind what we're doing here is very similar to how we added fields here for what were the receivers, the tight ends, the running backs. We're going to do the same thing for what the defense is doing here. So looks like that only took 20 seconds to run. Then we have to pull that information here into the data set. Let's call this receiver defender. We want to bring in that receiver data summary and then the defender summary. But we only want certain fields out of this. So I'm going to cut this down. I want the NFL ID. I want the fields that we made for CB, LB, BL, and S. On is still going to be that NFL ID. Oh no, what I want to do, I want to do game ID. Go here, play ID. And then this should be the same. Game ID and play ID. That ran quickly. Let's just look at the data set, make sure it's coming through the way that we want it to. Interesting. Okay, let's look at the position data because not all of them was just coming through. Well, let's come back to your question. I was just messing around with the data set and the frequency of pass coverage. Is there a reason why the Cover 3 double cloud have more yard gained than others, but it's only been used like 4 times? I wouldn't know without having more specifics in terms of the data table breakdown that you're here. Uh, this yard gain, I'm assuming, is going to be a field in the data set itself. Because my guess is when you see something like this, it's just because there was a big play, like a broken coverage or something that happened in these. So I'm seeing, or at least it's only been used 4 times, but I'm wondering if this was like a defense that was used against Hail Marys and had given up a few times, or depending on how you calculated your yard gain here, if it only been used 4 times, but you're doing something like an average and there were a few outliers here, that would be why this would be coming up. If it's flat yards gained, then it just may depend on how many times all these coverages are in the data set itself. So I would look at potentially how you have grouped the data in terms of this yard gain, just making sure it's like an absolute yard gained versus an average. And then if it is an average here and there's only 4 times, well, it's likely that those 4 plays, some of them have been outliers. If it's in terms of the absolute yard gain, then look in terms of the number of coverages here and see how many times that they all come up. And is that truly a good indication uh, of how the data set is or how the data is being represented? Let's come back to here where we're going to look at the player position data. Okay, so there's no D line, it looks like. There are CBs, but it looks like there are things like defensive ends and defensive tackles in the data set. And the linebackers, you have inside and outside linebackers. We've got the defensive line should be taken care of. The linebackers, we see cornerbacks, but then there are, two types of safeties here as well. So we've got the free safety and the strong safety. You see defensive back and a linebacker here, but only once or twice in the data set. Another thing here I missed is nose tackle. So then we need to come here and update this. So we have CB, we have ILB, BE, BT, FS, and SS. So this will take much longer now that it has to read through the data set over and over a few times. There we go. I do this. That's much more representative of what the data sets should look like. And now instead of receiver defender summary, or instead of receiver data summary, we want the receiver defender summary here. Great. So now we need to then also add those same fields here to the models. That means we need to add it to the categoricals as well as to the overall number of variables. We run through here. I don't think we need to update it afterwards, do we? So it takes a bit longer, but it does not add significantly to the model accuracy. Like we were just over 29%. We added about 4/10 of a percentage point to the prediction by knowing that. And we can still see here there's a wide variance in terms of knowing or predicting correctly versus what we see here. And so let's bring up that code for the prediction matrix. And we'll see what it's doing. Here. So pull that up. What's happening here? So there are more predictions to make, and we are seeing a large amount of the time it's predicting a go route, even though it's not actually a go route. Very similarly here, it's having trouble differentiating between a flat and an angle route in terms of what's a good separator to make its predictions. Um, if you look here at Go, it heavily messes it up with things like hitch as well. So we don't have enough good information here on what we're feeding to the model in terms of getting better predictions this way. Let's go and visualize the data a little bit here and just see if there's, if we can just look at it and try and get a better idea of what's happening here. So let's do this. Let's do create a figure, 12 by 6. And the idea here is that I can take, what do we call this, receiver data. Let's just look at the formations versus the routes ran, basically. So route ran, all this receiver routes by formation. And so now the X is going to be the offensive formations. The count for those routes. Let's show. Take a second for this to run. Let's see what happened here. Value after this must be iterable, not an int. So do I have, let's just do this. Receiver, right. Oh, formation is not here. Oh, that's why. Offense formation, not offensive formation. If I do that, good. I know why. Figure and then big size. There we go. Delete. Okay, fixing that up. You see here, most of the pass plays would run out of the shotgun formation. And you can see the majority of the routes here were go routes. Then go, flat, and hitch routes. And just kind of generally speaking, even out of the empty backfield here, similar things happen. Similar here for single back, but a little more of this. It looks like the cross route. So doesn't particularly tell me much in terms of helping the model. Let's just call this visualization. Try and look at the defensive coverage. Do I have that in my data set? I think I do. Go look at the data table. Yes, from the play data. So we need to go get this out of the play data to know the coverage. But if we're the offense, we won't necessarily know the coverage beforehand, so I don't want to incorporate that. It'd still be useful in terms of looking at the visualization. So let's go. We've got play ID. Yeah, so we can just merge that in. Got receiver, data enhance. This way. So we're going to take receiver def data. But we're also going to merge in plays, play ID, or game ID and play ID. And then on, this is now game ID and play ID. See if we can pull that together. Right, that needs to run first, then this. Double bracket. Gotta stop making that mistake. All right, so then let's look at the pass coverage then. So it's going to be very similar here. I'm just going to bring this down. But instead, I want to look at that coverage. It needs to be much longer. Let's do this. So this isn't offensive. This is defensive coverage. And let's add a rotation to this. Then we can read them a little bit better. All right, so what we're starting to see here is that this looks very similar to the offensive formation here. There are a lot more defensive coverages being thrown, but not where we're still having kind of the same breakdown, where there's a lot of go routes, flats, and then hitches with these cross routes mixed in. And so it probably means that for the most part, the models are going to try and predict these because it doesn't have enough information otherwise to differentiate why it was doing the different routes on the given play. So if I look at what I've got here, we have all the defenders listed out, but it didn't really add much in terms of predictive power. If we know the pass coverage now, does that change what we get in terms of the prediction? We're going to try and add this. We'll go back and remove it. This becomes a question of, even if we know the defense, does that particularly help the model in terms of the explanation? My guess is it's not going to add a large amount to what we're seeing here. Is it would mostly be the same? Clean some of this up while this is running. We're starting to see here now, it's starting to get longer, and you can see it barely moved that average, right? Just knowing the pass coverage did not particularly help the model outcomes here. So we had, was it 29% accuracy before, and now we're up to 29.7. Rerun this real quick and see. While this is running, I'm just going to take a look at the data set and see if there's anything else that can quickly come in. Yeah, so it was 29.54 and then 29.70 when we added that in. So even knowing what the defense is going to do, it still doesn't help the model all that much in terms of its actual predictive power. So we know the individual player helps the model. But still not enough to really improve the performance considerably, right? Because there's typically 3 to 5 receivers on a play. We can know one of the routes with this current accuracy. Maybe we'll know one of the routes. But overall, that's not particularly helpful. I was kind of surprised. Like knowing the pass coverage did not particularly help the model. But I guess that's because you will have, like I said, 3 to 5 routes per play, even though they're all under that same coverage. The Go through the data list quickly and try and see if there's anything else here we could pull in. Yeah, nothing jumped out to me as I scan over the data set here. Let's see. Penalty yardage. That's not going to be useful. That's result play action. I wouldn't know that before the snap. I guess the offensive team would know if it's play action or not. Let's see. Not particularly seeing it here, or at least anything quickly to be useful to add to the model. Yeah, I'm not seeing anything that would help us in terms of predictive power. We know the defending team. We know how many players are on the field. 2, 4, 6, 7. There's 7 groups there. If I look, random force is 27%. I guess let's see if this helps the other models. I know it's going to take a little bit to run, but maybe it can help those models out, knowing who the defenders are, or not who the defenders are, how many defenders are there of a given group on the field. We'll run it with the player data. Those got worse. Oh, the other thing is adding that to the decision tree here, because we had not had those before. So let me go up and pull those down. Take those, bring them down to the division classifier. It's here. Rearrange this. We'll run the first one. We'll skip this. This was we were pulling out Tampa in particular for the data set. Two things running versus that upgraded logistic regression model. Then going through the support for vector classifier and the random forest. We'll have about 5 minutes here. If people have questions to drop into the chats, then we can do that. So let's, like I said, we have about 5 minutes here. I can answer any questions that people have. I just realized I missed this message before from HeadGig. I was looking for support with Python plugin implementation for Blender. Sorry, I don't really use Blender here. You had a follow-up question then of, are you into learning AI stuff? Or I assume stuff, and that's just a typo. I would say yes. My name is Joe, the AI guy. It's my day-to-day job is working as a senior principal data scientist. So a lot of my work is on responsible use of AI in the company, and so um, making sure that the people that are the AI tools that we are building are done in a way that is safe and secure of the customers that we have. So that way nothing could potentially get leaked out in terms of what they're doing. So right now, a lot of my work is focused on building tools using LLMs. Most basic thing that we had done, we had built a chatbot, but that was updated with data specific to our company. That's called, the process for that is called RAG. So it's retrieval augmented generation. Basically, you're telling it to only use the data that you have provided to it. And so in doing it that way, we have it specifically set up that it only pulls from our data set. It will not try and infer any information that it would have otherwise. And then a lot of my work right now is focused on agents. So building essentially tools for the agents to use. So that way we can kind of integrate things into a single interface for users to, or for our users or customers to use it. So in the case of the chatbot, being able to go out and pull the right underlying data set to use for it, depending on a variety of information from anywhere in the website. So it has to understand what is actually being asked of it, and then going to that right data set, pulling it, and then using those right tools in terms of generating its response. Hope that answered your question. I know that was from about 15 minutes ago. Let's see, we're still running. Is it completed? No. The challenge here, right, as we add more and more columns to the data set is that it's going to take longer over and over again, especially the one-hot encoding step. So, as we added those cornerback DB fields to it, it now makes the process take longer because it has to transform the data set over and over again to handle those. And then it has to go through, build the model, make its predictions, and then evaluate those at the end. So you can see here, it took about 6 minutes. The support vector classifier is up to about 29%. So it's just about matching the output that we get from the logistic model here. But you can see in terms of the time to run, it only takes 30 seconds for the logistic model to run versus this support vector classifier. And that's just because this is trying to, its approach is a bit different from the logistic model, where logistic is very basically just trying to say like yes or no to a given answer. And then you're going to have random forest here, which is going to take longer. It'll probably be in that 6 to 10 minute range as well. What this is doing is this is trying to, it's going to go through, it's going to make a groups of about, not groups, it's going to try and figure out the 100 best estimators to build its model off of, and then use that to go ahead and make the predictions. We'd seen before its accuracy here was only 27%. And then once we added the player data, you can actually see how much this hurt like the logistic model, because now its accuracy fell to 20%, 21% from 27%. So like knowing who the players were on that significantly hurt its outcome here. Take this even further, we would have to then do the same process for this model to not only know who the players are, but now do we include this information? After the random forest runs, it's going to go through here and go to the decision tree classifier, because that's what we want it to fire off next. And just to give an idea of what I've got in terms of compute power, this is not a high-end machine by any means. This is a five-year-old gaming laptop. Basically, I wanted to have a GPU in it, and so anything that had a GPU is classified as gaming in terms of the laptop space. So it's got a what is it, a GTX 2060, I think, 8 gig version. And then the laptop itself has 16 gigabytes of RAM. So it is not um, high end by any means, and the technology is a bit out of date. I think, like I said, it's like 5 years old. So it's not that I'm running a supercomputer in terms of what you could get off of something like AWS or Google Cloud. We're just using kind of what we have available in terms of the laptop, so it's nothing overly powerful or anything like that. So here we'll see. It took about 3 minutes. 27% accuracy now. So not a large boost. If you remember before as well, this was a hair under 25 or 27%, if I remember. So it's not like it was a large benefit knowing the uh, count for the defensive players. So now it should be going into the decision tree, which will be pretty quick. And that accuracy is 20%. Not great. Let's see what it's doing here. It's really, yeah, it's only predicting like 3 or 4 groups. There's some that it will do sporadically, but it's not doing very well in terms of predicting much variation. If I had to guess, I'm going to say it's probably doing the same thing here. Well, that's a little bit better in terms of how it's breaking it down. So the player, knowing the players is being pushed further down in the tree. So let's come back to this part here, where I had set it up so that way we can feed it a group of different depth sizes for the tree and see if that will actually help us to get better results from the model. So it's going to take a little bit to run through. It won't be too long to go through each step of the way here. We had seen what the 8 took about 0.6 seconds, but it's going to have to go through all 50 here. So I would imagine this is going to take like 2 to 3 minutes because it's going to take longer as you get into the larger data sets. But the hope here is that we'd seen this before where really only knowing 5, letting it only go 5 deep was providing a bunch of information, or was providing the most information to the model. And I'm hoping that this will get larger or get better results further down in terms of the classifier, so we get a better idea of like what the actual splits are. Because if you leave it at only 5, it's going to be very arbitrary and not overall very good predictor, given that we have, what is it, 10 different classes of outcomes. And the trade-off is if you let this go infinitely large, it would overfit to the model as well. So it wouldn't do very well when you feed it new information. We'll let that go for a moment or two. And then once we know what that new depth cutoff is, we can feed it into here and get an idea of how it's actually breaking down the data. What we see here, it started to actually use the formations, but then you see a receiver is the next best split after that. So at least for one side of the tree, knowing most of the oh yeah, the majority would not be that receiver. So it's not a good breakdown. But then that means like for this player, it's very straightforward, I would say, in terms of knowing what route they're going to run. So if it's single back formation and this receiver is on the field, right, then there's no running backs. This is the groups, and then you can see, oh, knowing other players gives more breakdown. So where is it? So here we go. we're not getting as good results overall. Like I said, we're now in that 20% range. And you can see here a lot of fluctuation around that. And you can see kind of towards the end, these are actually starting to get better predictive value. So if I go, just give me the SNS. Box plot. It's why am I blanking on it? For the plot here. I want to go back to this visualization. So what do I got here? I got bar plot. I want a bar. I want a dot plot, basically. Seaborn. Scatter plot. So we got better results here in terms of, you can see, what is this, about 43 or so. I change this. It's going to vary slightly, but it should give us a far better breakdown. You can still see it's heavily favoring predicting a go route versus anything else. I'm afraid of what this chart will look like. So again, knowing the formation, heavily influential, but then also immediately after knowing the certain receivers. So I guess not particularly shocking. One of the things I am curious about is if we come back here, we go back to predicting run versus pass, but knowing this information and the defending team as well, how much this affects the model performance. Because we were at 75%, we did not have as much detailed information there. Yeah, and it's going to take a few moments to put together all the steps here. Let's do this, and this is where we'll kind of wrap up for today. Is we'll come back to let's do it after here. So just revisiting run versus pass, we're going to do logistic and decision tree with updated fields for players. Not what I wanted. That's fine. Go up here. I have these, right, as the base for the fields that I want. Those are 1. This is 2. This is the decision tree. Then let's go up here. Logistic. Very much the same thing here. This taking too long does not particularly add value. At least in terms of what we're trying to predict. Get what our actual classification score is. Wait a second. I did not go back into pass. No, rush. Right. Right, because the receiver data is only going to have passes. Okay. I need to go back and do this for. Okay. We do go back and add position counts to the okay. So we'll do that for next time because I'm out of time for today. What we're going to do is next time we'll come back, we'll finish this up. We'll just revisit the run versus pass, see if adding these player counts will help it, as well as the defending team information, to see if we can get better accuracy there, as we've been at 75%. I would hope that this would help to push it over a little bit towards 80%, if not more. And then what we'll do here is I will end this stream in about, I'd say, probably 5 minutes or so. It'll come back online where it will continue the AI agents training the model for our Pokemon reinforcement learning experiment. And one of them had gotten glitched out because it had produced or had purchased too many Pokeballs at a time. So I need to go back and fix that uh, as well because I had given it basically infinite money. Given it like I think it was 600,000 or whatever, which is just far too much because it will keep trying to purchase over and over again, get locked in that glitch. So what I'll do is I'll set that value much lower to be in that 10,000 range. That's really all it should need at a given point in time, and then that way it can keep progressing. So that's all for now. Like I said, thank you for those of you who came here. I know we had a lot of people in and out today and some questions, which was nice. And then um, I'll bring that stream back online. And then the hope here is that I will have time tomorrow as well. We'll come pick this right back up from where we stopped here today. So for those of you that are seeing this, thank you. If you have any questions about what we're doing or want to know more information, please feel free to join into the chats or leave comments on the videos so that way I can come back and answer them. Thank you, and have a great day.